Hello guys, today we're going to be solving a LeetCode question called binary search tree right side view. There's two types of traversals which first come to mind whenever solving tree problems or graph problems. Let me go ahead and write them out. One of them is going to be called depth first search. Oops, let me go ahead and undo that actually. So one of them is going to be called depth first search, and another one would be called breadth first search, right? That's just a little shortcut for it. Um, okay, so let me go show you the difference. So I'm gonna go ahead and just draw out depth first search right here. All right, so depth first search is kind of just like, okay, let's just say this is, let's say nodes, right? This is 5. One of them is going to be like 3. This could be 6, and we could just keep on splitting. This would be 1, 2. It doesn't even have to be a binary search tree. It could be any sort of tree. Let's just make this 6 again. So depth first search will kind of just search. Let's go in order. Let's say this is going to be it'll mark. Actually, let me use a different color. Okay. Okay, let's go ahead and use green. Green's a nice color. Okay, so this is going to be marked as 1. Ooh, actually, a depth first search would have something kind of just like a, let's see, this is like visited list. Let's call this visited. Okay, so we're gonna cross 5. We put 5 in this list, right? Then we'll do 3. Put 3 over here. Then 1. Then it'd go 2. Then it'd go 6. Then it'd go 6 again. Then 7. You see how we traverse that? Well, let's go ahead and show you the breadth first search. It would actually look different. It would traverse it this way. So breadth first search kind of goes broad instead of close. So let's go ahead and just draw that out. Let's just say this is 2, 3. It doesn't really matter what you put. 4, 5, 6, and then 7, right? Okay, so for breadth first search, I'm gonna go ahead and just have this say just a list right here. So we're gonna start with a 1. I'm gonna try to actually use a different color. Let's go ahead and use blue. Okay. So we'd cross out number 1. We'd put it on our seen list. Then we'd cross out number 2. Right? But instead of looking at number 4 or number 5, we're actually just going to look at number 3 because it's also known as level traversal. So we go level by level. See, for example, this is level 1. This is going to be level 2. And this is level 3. Right? So, okay, so we first searched the first level, and we see that everything in the first level has been seen. So now we go to level number 2, which has 2 nodes in it, which is 2 and 3. And now that we've seen all of that, we go to level 3, and let's go ahead and do that. So this is going to be 4, good 5 right here, 6, 7. All right, you see how in breadth first search we go in level. Well, depth first search we actually do not go by level. We go deep. So this we'd start over here. Then we do 2, 3, and then 4, 5, 6, 7. Right? You kind of see that. Well, this is kind of just kind of in order. Well, when you look at this question, right, which just says binary tree right side view, um, do we want to do a depth first search or a breadth first search, right? So basically, if we have a tree like this, this is one of the trees, for example, right here. We can see that we want to return 1, 3, and 5. Just because if we're standing on the right side right here, this is us, and we're kind of just looking at the tree. What do we see standing on the right? It might just be whatever's on the right side, but that actually is not true because I could give you a counter example right here. We could have a tree of just like, let's say that's the root node, 2, 3, 8, let's say this side is like a 3, another a 6. This is like a 2. So what do we want to return from this, right? So we could just say that this is level 1, this is level 2. Okay, this is level 1, this is level 2. I kind of fucked it up, but this is level 3. Wait a minute. Let me just redo this tree actually. So we could say that that's 2, 3, and then 4, 5, 6, right? So if we have this tree, this as our tree, what we actually want to return for our result, it would be 1, because you see that from the right side. It would be 3, because you see that from the right side. Then it'd be 4, then 6. Because we see when looking from the right side, we don't see number 2. We cannot see this. We don't see it just because 3 is already covering it. 4, we can see this because there's nothing to the right of it, so nothing's covering it. And 5, we do not see 5 just because 6 is already covering 5. So our output array would look like 1, 3, 4, and 6. So our job is go ahead and try to find an algorithm to solve this. Looking at this, we could see that we could kind of search level by level, right? And by doing that, we see that the element to the furthest right of our breadth first search would be the element that is on the far right, which is the one that we see from the right side view, which is part of the problem. So to write the code, we could kind of just make a breadth first search, right? So we could just breadth first search. So I would say number 1, breadth first search. Number 2, at each level, return the rightmost element. Right? Does that make sense for an algorithm? Yeah, I think that's good. So we could just run a breadth first search, and a breadth first search is also known as level traversal. Right? So at each level, right, because we were going to visit each level by level, we're going to return the element which is at the rightmost. Okay, so let's go ahead and try to write the code for that. So for breadth first search, what we actually need is a queue. I could draw out the queue and what it would look like, but let's go ahead and do that first. So we want to go from collections, go ahead and import the queue. And let's just go call queue is going to be equal to dq. Okay, and let's go have something called like a result list. Okay, now we could say q dot append. Let's go ahead and append the root. And we could say while I want to say while current too. Current is going to equal to root. So while current or q and q, while there's currently something and there's something inside the queue, we should just go ahead and just go level by level. So I'm gonna say let's get the length of queue is going to be equal to the length of queue, and we could say for index in range length of Q. I want to say node is going to be equal to let's say Q dot pop left, right? It's kind of just getting the first element there. Let's say if node, if there is something in that node, then we want to kind of just add its left and right childs. So if node, then just go get the level. Right, this is whatever element is inside the level. So the length of Q is going to be length of Q, okay? So there's going to be that level. And for index in range length of Q, node, we want to pop it to the left. If node dot left, then we want to just add it. So I want to say Q dot append node dot left. I want to do the same thing with the right. If node dot right, then I'll say Q append node dot right. We should also add it to the level. So I want to say level dot append node. So after the index, after we loop for every one of those, we could assume that the level. So I'm gonna say if level, then go ahead and just do answer dot append level. But we don't want the whole level. We just want the level at -1. Okay. I want to say if node, then we want to append it. Okay, now what we want to do is actually do, we want to pop the result. We want to get the result. So we could just return result. But we should actually call it first. I'm gonna say go ahead and run this. What do you have? Instead of calling answer, we'll call it result. Okay, let's see what's wrong. We want just the value. Alright, and that's how you solve it. That is how you solve binary tree right side view, which is a medium problem. I go ahead and just write this. I could write out this so you could go ahead and visualize it. But my dad just came home from work, so I'm just gonna go ahead and end the video there. See you guys later.